Still in the introduction, I want to see with you the benefits and the limitations of this technology. We are still in the introduction, but this time I want to discuss benefits and limitations. So let's start with the stress distribution that you find typically in a transport structure, more precisely in an airplane. So you have two joints here. You have a riveted joint and you have a joint very similar, but instead of a rivet, we use an adhesive, all right? And this is a typical joint that you see in airplanes. Here is the fuselage. It's what you see from outside. And you see the parts of the rivets from outside. And inside you have this stiffener, okay? To give more stiffness to the structure, because if it was only the skin, it would be too flexible. With your hand, you could push down the fuselage. All right. So then, how this is being loaded in service? Well, you have the internal pressure, okay, that is being applied when you fly. And if you look at the stress distribution corresponding to this loading, which is represented here, so with the internal pressure pushing on the joint is going to be tensile loaded, which is what is shown here. How is the stress distribution along the width? Well, you can see that next to the hole of the rivet you have high stress concentrations, which is not nice in terms of static strength, but even worse than this is not nice in terms of fatigue, because you will have here crack initiation and then propagation. Now, if we look at exactly the same, but this case adhesive bonded, first of all, we have a smaller non-reinforced area, so we have a stiffer joint, which is nicer. And then, for the same loading, how is the stress distribution along the width? As you can see here, is perfectly uniform. There is absolutely no stress concentration. So the adhesive can make a better use of the bonded area, and even if it's not as strong as a rivet, because it uses the whole area, it takes advantage of the area, it compensates with the area, and in fact gives a higher joint strength. So that's really the secret of this technology. It's true that the material itself is very modest in terms of strength, but because the load is spread over a large area, it gives a high strength. So very, very important slide, this slide number 2 of this introduction section, don't forget it. Because you have a better stress distribution, then you have better fatigue strength, you don't have the stress concentrations. And this is what is shown in this graph, where you have the stress being applied versus the number of cycles. We are talking about fatigue, so cyclic stress, the stress is not very high, well below the yield strength, but it's applied repeatedly, and after a while, after some cycles, the material will start to damage. And depending on the configuration, the type of joint, some withstand better than others. And you have three situations, three cases here. You have the case of the riveted joint, which is here. Then you have the case of the bonded joint, which is the blue line. And then you have the case of the metal only. There is no joint, basically, and it's the green curve. So what we can say really is that the bonded joint is nearly as strong as the case where you don't have joint at all. So very, very impressive. Whereas the riveted joint is well below. So for the same stress applied, or for the same number of cycles that you want, the stress that you can apply for a rivet is much lower than the stress you can apply for a bonded joint, or the case where you don't have joint, any joint. So really very impressive result. Then you can join dissimilar materials. You can't do that with all the joining technologies. For example, with welding, you cannot weld aluminium with a plastic. It's impossible. But you can adhesively join a metal with a plastic or with a composite. Very, very easy. It's able to join thin sheets very efficiently. That's a very important point, because this technology does not make sense for very, very thin materials. Like take these two parts that you want to join, they are quite thick. And if you do a butt joint like this, the joint of course will fail because the adhesive has a strength much lower than the substrate, and it will fail. You can think, okay, I can do an overlap for the adhesive and take advantage of a bigger overlap. The problem, even like this, the thickness of the substrate is still very, very high, and it will probably fail at a low load again in the adhesive. Doesn't really make sense. What makes sense is to use thin sheets. Again, if we do this, doesn't make sense. It will break in the adhesive, low strength. But now if you do this, now the area, which is the same as before, is very high for the adhesive. But since you have a very thin sheet, the strength that you get from this area times the strength of the adhesive is comparable to the strength you have when you use the strength of the substrate times a very thin thickness. It's comparable, and sometimes it even breaks in the substrate. So really, it makes sense when you use thin sheets. And this is the most common joint, single-up joint. But in airplanes, in cars, in trains, does it make sense? Yes. In all these structures, in fact, we are talking about thin sheets. There is not things like that. Things like that don't make sense in an airplane. Why? It's too heavy. So they need to reduce the thickness. Okay, if you reduce the thickness, then adhesive bonding is the best. Okay? Frequently, the most convenient and cost-effective joining technique, arguable but many times true, you have an increase in design flexibility. You can even invent new materials like the honeycomb structures, the sandwich structures where you have a strong skin, you have a foam or a honeycomb in the middle, and then the two are bonded with an adhesive film. So this was invented, or it's possible, because you have adhesive. Imagine doing that with a rivet or with a bolt or with welding. It's impossible. You have smooth shapes, that's true. You don't have that marks due to bolts or rivets or welding. You have a continuous contact between surfaces. This is good in terms of mechanics, but also good in terms of sealing, in terms of vibration, in terms of corrosion. It's all good things. And in general, it reduces costs. Again, this one might be it might generate controversy, but in general, it is true. Okay, so this was the benefits, but of course, you also have limitations, disadvantages when you use the technology, and it's important to discuss them. Probably the most important one is this one. It's the peeling loads, really the major enemy of adhesive bonding. And to make sure that you don't forget this and you understand really what I mean, I'm going to make a small demo with an adhesive tape. Okay, very common adhesive tape that you have all of you at home. Let's try. Let's play a bit. So first of all, I want to remove a piece of tape, and the loading I'm applying is this. I'm peeling the tape, and the effort I'm doing is virtually zero. Okay, because as you can see, I'm applying my load, the whole load in one line. The resistant area is really small, and I can peel off very easily. Okay, now I'm going to do or use exactly the same material, the same substrate, the same adhesive. It's a pressure sensitive adhesive. You have adhesive here, it's tacky, but I'm going to load in another way, and you are going to see the difference. Okay, I'm going to do a single up joint, so I'm going to take a piece of the tape. Okay, and I'm going to put on top another piece to create a single up joint, and I'm putting the part that has adhesive on the part that has no adhesive. I'm not cheating, because before this was the case also when I peeled the tape. So I just built a single up joint with you, all right? And now I'm going to load it like this. So the substrate will be tensile loaded, but the adhesive will be shear loaded. And the resistant area for the adhesive is quite long. It's the overlap times the width. Okay, overlap times the width. Huge resistant area. Whereas for the substrate, it's very thin, the thickness times the width. The substrate is much stronger than the adhesive. But now, in terms of resistant area, because the adhesive has a much larger area than the substrate, we are going to see if it's still the weakest point. So I'm going to load it. I'm loading. I'm making a lot of effort at the moment, I can tell you. I'm nearly fainting. And it failed. And it failed outside the joint. It failed in the substrate. So we go from a situation where the adhesive fails very easily to a situation where the adhesive is strong enough to provoke a failure in the substrate. All this because I understand what joint design is. I'm a good mechanical engineer. So, what's the moral of the story? Adhesive, very weak materials. What do you do to take advantage? You use a large bonded area and you load the adhesive in shear. That's the philosophy behind all adhesive joints. Reduce the peel loads, increase shear stress over a large bonded area. That's it. So, peel exists when one of the substrate is flexible, but you might have two rigid substrates. Imagine you have this. You put adhesive and you want to peel. It's the same kind of loading, but because they are the two rigid, we call it cleavage. It's the same family, okay? So what you should do to avoid peel and cleavage? Well, if you keep loading something like that, then you have to make sure that the load is perfectly aligned. If it's slightly disaligned, you have cleavage. If the thickness is not perfectly uniform, you have cleavage. So this is possible, but it's possible or it makes sense only if the substrate has a strength similar to that of the adhesive. And in general, it's not the case. So, not really a good solution. This is the solution. You do an overlap, okay? And then you have a huge resistant area for the adhesive and a small resistant area for the substrate. This one can be stronger, okay, it's true. But because for the adhesive we are a large area, this might be enough even to break the substrate, which is what happened in the case of the tape, okay? So please don't forget this. With this, you will be successful in joint design. That's the rule you need, basically. But there are some other things we have to list for the limitations. We are talking about a polymer. Polymers, they don't like temperature. They don't like water. So you have to be careful with these conditions. Adhesives are always applied in the liquid state. You will see that in the theory of adhesion. And then they harden. So you need an equipment that will keep the two together until the adhesive hardens. In general, to have a good adhesion, you need a surface treatment. You will see also this in a theory of adhesion, surface treatments, which is an additional step in terms of manufacture. Many adhesives, they harden at high temperature. That means you need an oven to heat the joint. Not very nice. Quality control, fortunately, there are many devices that can detect non-destructively defects in joints. But there is one defect that cannot be detected, or nearly it cannot be detected, which is a weak adhesion. And finally, there is not a universal failure criterion that is applicable to all joints, no. There are many analytical models, many failure criteria, and this sometimes is a bit confusing, and it's a limitation because the engineers might be afraid to use this technology. But in fact, it's not that complicated. I will show you when we talk about joint design with half a dozen models, we can already design a lot of situations.